Okay, so when we're talking about our space physics, we have to start with talking about our sun in detail. Okay, so when you are talking about our sun, what do we know about the sun? Sun is actually a star. We generally consider the sun to be a star of medium size. Okay, we consider the sun to be a star of medium size, generally speaking, and it is actually uh, present at the center of our solar system, and it consists mostly of hydrogen and helium. Those are the two major gases that you can find inside of it. It is a ball of gases that is at a very, very high temperature and really, really high pressure. So a ball of gases that are all pulled towards each other or compact in the form of a star, and they have a really, really high temperature and really, really high pressure. Majority of the gases on your sun are hydrogen and helium. And the sun is responsible for producing two electromagnetic radiation, right? Actually, three. Infrared. Infrared radiation is produced by the sun. The sun also produces ultraviolet radiation, and of course, it produces visible light. We have to talk about in detail how the sun is formed, how our sun is actually formed, and then we have to go ahead and talk about how the sun actually produces energy. So our sun, how was it formed? So there at one point initially, the sun was just a large cloud of dust and gas particles. That's it. You had hydrogen, you had helium, and you had your dust, and it was just a large cloud of dust. That's it. This cloud of dust was known as stellar nebula. Now, what happened that because of the gravitational forces, the dust particles and the gas particles, they were all attracted towards each other. And the gas particles, the dust particles, they all started to come closer and closer to each other because of gravitational force. Now, this was not a quick process. It wasn't like it just happened over, a few days. No, this process took many, many years. But in those many, many years, the dust particles and the gas particles, they sort of kept coming closer and closer to each other because of gravitational forces, until the particles came so close to each other, they became held together so tightly that it caused a huge increase in temperature and pressure. Right? So you were compressing the gas particles. Think of it. When you're compressing the gas particles, you will of course increase the pressure. When you will increase the pressure, the temperature also increased. And this led to nuclear fusion. Nuclear fusion is the reaction that takes place on the sun's surface. I will explain to you about nuclear fusion. Nuclear fusion is the reaction that takes place on the sun's surface, and this reaction is responsible for the huge amount of heat that is taking place. So what was happening? There was an increase in temperature and pressure because of the particles of gases coming close to each other. That led to nuclear fusion. What was nuclear fusion? The hydrogen nuclei started to fuse with each other to make a larger nuclei. So remember, if you've done atomic physics, you must have studied about nuclear fission. That is what we use in our nuclear power plants. Nuclear fission is when we are breaking down a nucleus into smaller parts, and in the process, we are releasing energy. That is what we do in our power stations. Nuclear fusion is when you are joining two nuclei together to give you a larger nucleus, and you're releasing energy in the process. We cannot do nuclear fusion on the Earth's surface because it requires a lot of pressure and a lot of temperature that we cannot generate over here. So we don't do nuclear fission, we can do nuclear fusion. Nuclear fusion nuclear fusion is hard because you're trying to push two nucleus together. Both the nucleus are positively charged, so of course they will repel. So you have to overcome the repulsion. You have to put in enough energy to overcome the repulsion that you can make them fuse with each other and end up forming a larger nucleus. So what happened that because of this temperature and pressure, nuclear fusion started. Hydrogen nuclei started to fuse with each other, and in the process they released a lot of energy in the form of light energy and heat energy. And that is when our sun turned into a young star. So this is how our star was actually formed, or this is how our sun was actually formed. Now, generally what reaction takes place inside our system? What is the reaction that takes place? Hydrogen reacts with hydrogen to give us a nucleus of helium, like this. This is the reaction for nuclear fusion, and in this process you are producing huge amounts of heat energy and light energy. Now, this is what happens to our sun. Then we have to talk about our stars, right? When we talk about our stars, where can we find our stars? Our stars, or when we talk about galaxies, galaxies are made up of many billion of stars. So different galaxies, we have Andromeda, we have Milky Way. All of these different galaxies are made up of billions and billions of stars. Stars are balls of gases. So there are hot balls of gases that can be found in our entire universe, and each galaxy will have billions and billions of stars inside. The galaxy we live in is, of course, known as the Milky Way galaxy, and our sun is present in the Milky Way galaxy, and it is the center of our solar system. Inside the Milky Way, you have many solar systems, by the way. Inside the Milky Way, you have lots and lots of different planets, lots and lots of different solar systems. I mean, the universe is so big, just you cannot imagine. You have your entire planets that we know, our entire planets, all the way up to Uranus. They are all so far away, like light years away, billion of light years away, which means that we are traveling at the speed of light, and it's still going to take us billions of years to get there. They are that far away, and that solar system is just a small part of the Milky Way galaxy. And in our Milky Way galaxy, we have many huge solar system like that. And then in our galaxy, we have other galaxies that have similar huge numbers of solar systems inside of them. So our galaxy is known as our Milky Way, and the star that we know is our sun. The other stars from us are really far away. The other stars from us are really far away. And I mean, so the stars that you can see in the sky, they are actually just like our sun, or they're bigger than our sun, producing a lot more heat energy. But since we are so far away from them, we are not able to see drops as dots, right? And so when we talk about it, when we talk about distances in terms of space, when we talk about distances in terms of space, in space we measure distance not as meters or kilometers, we measure it as light. Okay, so when we're talking about it, we're going to, for example, say that this planet is 10 light years away. That means that if I'm traveling at the speed of light, it will take me 10 years to get there. So when we talk about measuring distances in our space physics, in our astronomy, we are always going to be looking at light. Now, we need to, of course, know about the life cycle of a star, how a star is going to form. The formation of a star, or how the star will form, is similar to how our sun was made. There's not a lot of difference in the starting process. But we know how our sun was made. But what happens after that? What happens once a star has been made? Let's go ahead and talk about it. So, what's a star is formed from interstellar clouds of gas and dust that contain hydrogen, right? So, what actually ends up happening? This, everything that we studied over here. The sun was found from large cloud of dust and gas particles. Just like that, any star, that was specific for sun, but any star is initially going to be made up of cloud of gas and dust that have hydrogen and sometimes helium inside of it as well. So generally what is going to happen, that the gravitational forces were, remember, they were pulling the gas particles together, that increases the pressure, and that causes nuclear fusion. When nuclear fusion happens, when nuclear fusion is going to take place, what will happen? Huge amounts of heat energy and huge amounts of light energy will be released. Now what is going to happen, that so the first star, the star initially, the star is going to be known as a protostar. Initially, the star is going to be known as a protostar. Now, what is going to happen? A protostar is an interstellar cloud collapsing and increasing in temperature as a result of its internal gravitational attraction. So what's going to happen, that the internal gravitational attraction is going to cause your cloud. Remember that cloud we were talking about in the beginning, the cloud of dust and gas. That cloud of dust and gas will collapse and the temperature is going to increase, and that is going to form the formation of a protostar. Now, what is going to happen, that once the protostar is made, now you have high temperature, right? Because nuclear reactions have started. Nuclear fusion is taking place. Because of that, huge amounts of heat energy are being produced. That heat energy will cause an increase in the temperature of the star. So what will happen whenever you increase the temperature of gases? Gases expand. So what's going to happen? Your star is going to expand. Now, the gravitational force is pulling the gases inwards. The high temperature is pulling the gases outwards. Eventually, the forces will balance each other out. Eventually, the expansion is going to become equal to the compression. Eventually, the expansion because of the high temperature and compression because of the gravitational forces, eventually these two things are going to balance each other out, and your star is going to turn into a stable star. So at this particular time, now your star is stable because now the gravitational force is equal to the expansion. The expansion is coming because of increase in temperature. Gravitational force is basically causing pulling the gas particles together, and the increase in temperature is causing them to expand. So what is going to happen, that when they will balance out, now the star is going to be balanced because the inward forces and the outward forces are equal to each other. So it will end up becoming a stable star. So initially what was happening, you just had gravitational forces. The gravitational forces made the cloud collapse and turn into a protostar. So initially there was only gravitational forces. Once the protostar is going to form, nuclear reactions will start. When nuclear reactions will start, increase in temperature will happen, and that increase in temperature will cause some expansion. The expansion is going to keep on happening until the expansion and the gravitational force are equal to each other, and now the star is a stable star. Now, this is where our sun is right now. Our sun is a stable star. Yeah, Monami?
Miss, could you explain the part after the cloud of gas and dust collapses? What happens?
After the cloud of dust and gas collapses, a protostar will form. Once the protostar will form, nuclear reactions will start, specifically nuclear fusion, right? When nuclear fusion is going to happen, this is going to cause an increase in temperature. When there is going to be an increase in temperature, so okay, going back to the protostar, your cloud of dust was collapsing. Why was it collapsing? Because of gravity, because of gravitational forces, right? Those gravitational forces were pulling the gas particles inwards. That is why the cloud of dust collapsed, because the gravitational forces were pulling them, all the gas particles, towards the center. Now, after this, this will increase the pressure, and as a result, nuclear fusion will begin. When nuclear fusion will start, huge amounts of heat energy will be released. The huge amount of heat energy that will be released is going to increase the temperature of the gases. So gravitational force is pulling all the gas particles towards the center because it's gravity. The increase in temperature is going to cause the gas particles to expand. So the increase in temperature will be causing the gas to expand. The gravity will be causing the gas particles to come closer. So they're both working in opposite directions. So eventually, the expansion is going to become equal to the gravitational forces. So the increase in temperature will make the gases expand. The gravitational force is going to try to, make it collapse. So eventually what is going to happen, the two forces will become equal to each other, and the star is going to reach a stable stage where the gravitational force and the expansion are going to be equal to each other. So your star is going to be now stable. Is it making a bit more sense?
Yes, miss.
Okay. So that is basically what is going to end up happening. So the star is going to end up becoming stable. When the star will become stable, that is where our sun is right now. Our sun is in the stable stage. Now, what happens at the end of the stable stage? When the stable stage is going to end, what happened? That if so, we are doing nuclear fusion, and for the nuclear fusion, we need hydrogen nuclei, right? We need the nucleus of hydrogen so they can fuse with each other and release energy. But the number of hydrogen nuclei or the number of hydrogen particles are limited. Eventually, we will run out of them. Eventually, we will have no more hydrogen nucleus left. That is the end of stable period. That is when the stable period is going to end up running out, when we have run out of hydrogen for the entire process. What will happen? There is no more hydrogen. Nuclear fusion cannot take place. Nuclear fusion cannot take place. The temperature will drop. The temperature will drop. What will happen? No more expansion. Temperature will drop. Expansion is gone. What is the only force left? Gravitational force. Because there's no expansion force to balance it out. All you have is gravitational force. The gravitational force is going to win, and the star is going to collapse. When the star is going to collapse, what is going to end up happening? The star is going to collapse. All the gas molecules will come close to each other. When all the gas molecules are going to come to each other, what will happen? It will cause an increase in pressure. You know that, right? When the gas is compressed, when any gas is compressed, pressure increases. So when the pressure is going to increase, what will happen? The increase in pressure will become so high that now the nuclear fusion will start again, but this time with helium. So first we were using hydrogen. Hydrogen ran out, the temperature dropped. No more expansion, only gravitational forces. Gravitational forces pull the star back. They start to compress the star back, which increases pressure. Increase in pressure causes the helium to start fusing with each other. The helium is going to start fusing with each other, and as a result, again, there is going to be an increase in temperature. So first, a drop in temperature, it will become cold. That will increase, that will compress the star. The gas is going to come together. The star is going to shrink. but that increases pressure. It increases pressure so much that now there is enough pressure for helium to start fusing, and the helium nuclei are going to start fusing with each other. And when the helium nuclei are going to start fusing with each other, what is going to happen? So hydrogen was a smaller nucleus. Helium is bigger. So it will produce even more energy than the first time. And it's going to release so much energy. It's going to release so much energy that the star will expand. The temperature of the sun is going to shoot up so much that the star will literally expand to much bigger than the original size. So whatever is the original size of the star before, when the hydrogen was there, compared to that, it will expand to a much bigger size. And what will happen? This is when we will say our star has turned into a red giant. So you must have heard the scientists saying that about our sun, that eventually our sun is going to become very big, and the heat of the sun is going to end up killing everything on the Earth's surface. That is what the scientists say. This is why it's going to end up becoming so much bigger, because it's going to turn into a red giant, because your expansion is going to be so great, because the temperature will be so high. Why? Because helium fusion is taking place. After this, the planet is going to stay as a, the star is going to stay as a red giant. But again, same problem as before. Same problem as before. Eventually, the helium will also run out, right? Eventually, the helium will also be gone. The same problem as before. Hydrogen ran out, so eventually helium will also be gone. And once the helium is going to be gone, now what is going to end up happening? So what is going to happen? What's going to happen is that, again, temperature is going to drop. When the temperature is going to drop, what will end up happening? That your star is going to turn into a dwarf. It is going to end up going to go from a red giant, and it's going to end up turning into a dwarf. It's going to end up turning into a white dwarf. It will only produce blue light and white light. And eventually, as it keeps on getting colder and colder and colder, it's going to turn into a completely cold black dwarf. So this is what actually ends up happening to our planet. Now, when we talk about what happens after this, after it turns into a planet. So after it turns into a cold dwarf, into a cold black dwarf, I said a planet, I'm sorry. What happens when it turns into a cold black dwarf? So when we are going to talk about it, right. So what happens to the planet, or sorry, what happens to the star also depends upon the size of the star. Okay. This entire thing that I just told you, Monami, this is for a small to a medium star. There are some stars that are very large. So what happens to a large star? A large star will not turn into a red, it won't turn into a red giant, it will turn into a red supergiant. So after the stable period is over, after this you had protostar, then you had stable period, and then you had red giant. For a big star, a huge star, you will have protostar, stable period, then it will turn into a large red supergiant. Now, what is going to end up happening? That the red supergiant can explode and turn into a supernova. This was turning into a white dwarf. This turns into a supernova. It explodes and it throws dust and gas everywhere. So a small star turns into a white dwarf, but a huge star is going to explode and it is going to turn into a supernova. And what is going to end up happening? From the supernova, you end up getting what you end up getting? So you end up getting, after the supernova is going to take place, after the explosion is going to take place, you will get a black hole. Okay, a black hole can form, a neutron star can form, a black hole can form, and a nebula can form. That nebula will have many hydrogen and it will have other elements inside of it. So you are going to end up, what's going to happen? The supergiant is going to explode as a supernova, forming a nebula. So it will form a nebula containing hydrogen and new elements, leaving behind a neutron star or a black hole at its center. So the neutron star or the black hole will be left at the center, and around it you will have a nebula which will contain hydrogen and other elements inside of it. Right? Then the nebula that we are getting, that nebula can then make new stars and new planets. So this is basically what the life cycle of a star is. So we start with a small, I'm going over it again. For a small star, we first have a protostar, then we have our stable period. After the stable period, what will happen? It will turn into a red giant. That red giant will turn into a white dwarf and a cool black dwarf. Now, sometimes what happens that the red giant, when it turns into a white dwarf, it also makes something we call planetary nebula. The planetary nebula generally is formed and it has the white dwarf at the center. So that can also happen. Once it turns into a white dwarf, the white dwarf can be present at the center and it can be surrounded by a planetary nebula. And that will eventually turn into a cold black dwarf. For a large star, what will happen? It will have a protostar, stable period, and then it will become a large supergiant. After supergiant, it's going to end up turning into a supernova. That it will explode as a supernova. It won't turn into a supernova. It explodes as a supernova. Okay. So it basically explodes. The exploding star is called supernova. I mean, the name of an exploding star is called supernova. After it explodes as a supernova, it will end up making a nebula and it will end up leaving behind a neutron star or a black hole at its center. The nebula can then go on and make new stars with new planets and everything like that. So that is how the life cycle of a star is. Any confusion in this? Anything you want to go over?
No, miss.
All right. So you need to know the stages of your stars pretty well. Okay, just give me 1 second. Okay. Now, another thing we have to go ahead and go over is our universe, right? So when we talk about our universe, we first need to talk about red shift. What is red shift? Okay. So what we can actually do is that when you and I are talking about the universe, when we are talking about the universe, we can go ahead and take a look at the movement of universe by looking at our wavelengths, right? So, we can go ahead and take a look at the wavelengths, and by looking at the wavelengths, we can tell in which direction the universe is actually moving.
Miss, wavelengths of what?
Sorry?
Wavelengths of what?
Of your
Wavelengths of
electromagnetic
light?
radiation. Electromagnetic radiation, right? Electromagnetic radiation, that's what you have in your solar system. So your electromagnetic waves, their wavelength, right? So I'm measuring the wavelengths of the electromagnetic wave, especially the visible light section. So from the entire electromagnetic waves, you have the visible lights. So from the visible light section, you can go ahead and measure the what do you call it, wavelengths of them. And by measuring the wavelength, we can go ahead and we can tell in which direction the universe is moving. Okay. So basically what happens that if the universe is, now there was a question. Okay, fine. I'll go into it. Look, there's a question. Is the universe expanding? Is the universe compressing? Or is the universe stable? Right? Is the universe moving away from us? Is the universe coming towards us? Or is the universe staying as it is? This is a question that the scientists wanted to get an answer of. They wanted to know that what is actually happening. Where is the universe going? What is happening to the universe? So they decided to find out the answer by using wavelength of the electromagnetic radiation, especially the visible light. Okay. So what they said was that if the universe is moving away from us, then the wavelength will be increased because the light waves will be stretched out. If the universe is moving away, if the universe is pulling away from us, if it's moving away from us, then the light waves will be stretched out and the wavelength is going to be increased. If the universe is moving towards us, then the waves are going to be squashed together, the waves are going to be pushed together, and as a result, the wavelength is going to decrease. And if the universe is not moving at all, then there will be no change in the wavelength. Now, what happened is that when the wavelength, so they said that if the universe is moving away from us, the wavelength is going to be increased because your waves are being stretched. This is known as a redshift. Why do we call it a redshift? Because if we look at the light waves, right? So blue light is going to have the shortest wavelength. Red light will have the largest wavelength. Okay, so we observe that the wavelength is changing. It's going from blue color towards red color. So that shows us that the wavelength is increasing. So we call that redshift. If the universe is moving towards us, what will end up happening? That we are going to observe that the wavelength is going to be getting smaller and smaller because the wave is going to get squished together. If the wavelength is becoming smaller and smaller, then we should observe that on our visible light section in our light spectrum, that the light shift is happening towards the blue side. That our color is shifting towards the blue side because blue side has a smaller wavelength. So that is known as a blue shift. Now, if you look over here, can you see these black lines? These black lines show the absorption of light by specific atoms in our star or in our galaxy. So let's say that 10 years ago, the scientists went ahead and they made this, they got this absorption spectrum. We call it an absorption spectrum. So they went ahead and they looked at the absorption spectrum of our sun, for example. Okay, they said, okay, this is the diagram we are getting. Our sun absorbed this particular light, our sun absorbed this light, and our sun absorbed this light. Fine, this is what we got. Then they went ahead and after another number of years, they again take a look at the spectrum of the sun, and now they observe that the sun is absorbing different wavelength lights. The sun is absorbing different wavelength of the light. It is absorbing wavelength that is closer to the red side. So they call this a redshift. That okay, the spectrum or the wavelength is shifting towards the towards the red side. The sun was first absorbing the light, blue light, but now our sun is absorbing red light. So it observed a shift in the spectrum. And since it observed a shift in the spectrum, they said that our universe is showing us a red shift. And that is how they came up with the theory that our universe is expanding. Is this making sense?
Miss, could you explain the part where the red shift and the blue shift once again?
Sorry, Monami, can you say it again?
Could you explain red shift and blue shift once again? Like, how do you find out?
Red shift is when the wavelength is shifting towards the, you have your visible light, right? You have, if you've done the topic of electromagnetic waves, you must have studied it. If you haven't, it's fine. We have to do the topic of waves. So we'll go over it, okay? But when you talk about your electromagnetic waves, you have basically your visible light. When you talk about your visible light, so in your visible light, what is happening? That we are making an absorption spectrum. The absorption spectrum, for example, we're making an absorption spectrum of the sun, okay? Now, what is going to end up happening? The absorption spectrum shows us that this is the wavelength that is absorbed by the sun. So this is the wavelength that is being absorbed by the sun. So when I am going to take a look at my spectrum, I'm going to take a look at my visible light, I will end up getting these black lines. The black lines are telling me, okay, this is the wavelength that is being observed by the sun. So if you look over here, the sun is, for example, first absorbing the blue wavelength, okay? Then after a few years, you said, okay, let me check again. What wavelengths or what light is the sun absorbing now? This time you observed that the absorption spectrum or the black lines had shifted. They had shifted towards the red side of the visible light. In the visible light, it was now taking red light. It was now taking red light, or it was now taking the black lines had moved towards the red side. Why? Because the sun is now further away. Since the sun is now further away, the wavelengths are more stretched out. Since the wavelengths are more stretched out, so in our visible light, we know that our blue lights have a shorter wavelength and our red lights have a longer wavelength. So we observe a shift in the spectrum, that first the sun was absorbing small wavelength and now the sun is absorbing high wavelength. So it's going from blue color to red color. It was first absorbing blue wavelength, which was of shorter color, and now it is shifting towards the right side, towards longer wavelength. That is known as red shift. If the absorption line, if the sun is absorbing a light of less wavelength, then the light will be towards the blue side. So that will be known as a blue shift. If the sun is, if your wavelength is shifting, so the wavelength that you're absorbing are shifting towards the blue side, that is known as a blue shift. And if the wavelength that is being absorbed by the star or the galaxy, whatever you're studying, it is shifting towards the red side, then it means that you are observing a red shift. So red shift means that the wavelength is getting, if you're observing that any galaxy that we're studying, that the light it was absorbing is now shifting towards the red side of the visible light. So that means that the wavelengths are getting longer and that galaxy is moving away from us. If we are observed that the wavelength that the galaxy was absorbing is now moving towards the blue side of the visible light, that means that the wavelengths are getting shorter, and that means that the galaxy must be coming towards us. Is this making sense? Do you need me to go over it once more?
No, Miss, that makes sense.
Okay, so our galaxy is giving us a red shift. So if you were to go ahead and take another galaxy and you decided to study the absorption spectrum, so you would, for example, see that first it was absorbing blue light. And then after a few years, you will see that it is slowly moving towards the red side. So that means that the wavelengths are getting longer between them, us, me, and the galaxy. So the galaxy burst is moving away from us. So that is what we can see in our universe. Our universe is expanding. Okay, so if you take a look at our universe, you will observe a red shift. Okay, and you are going to see that the uh, light from distant galaxies is red shifted, and the further a galaxy is from the Earth, the bigger the redshift is. So further the galaxy is away, the more your wavelength will be towards the red side. So for example, if you have two galaxies and you want to compare which one is far away, so you can take a look at the wavelength. So the one that is far away is going to be closer toward the red side. The one that is closer to us will be more towards the blue side. Now, there are two things that we know. One thing that we know is that the universe is expanding and all the galaxies are moving away from us. The second thing we know that greater the distance a galaxy is from the Earth, the greater the speed at which it is moving away. So for example, you've got two galaxies, right? This galaxy is close to us, galaxy number 1. Galaxy number 2 is far away from us. So the galaxy number 1 will be slower. Galaxy number 2 will be faster. So greater the distance, the further away a galaxy is from us, the faster it will be moving away. The faster it will move away from us. So greater the amount of distance between us and the galaxy, the greater the speed of the galaxy as it moves away from us. So those are the two things that we know about our universe. Our universe is expanding, which means galaxies are moving away from us. And secondly, that greater the distance, the further away a galaxy is from us, the speed of moving away will also be greater. Is that making sense?
Yes, Miss. Miss, how long does this take?
How long does this take? This takes. It's been happening constantly. It is. If you want to, it's not something that is contained by time. It is something that is happening constantly. It is something that is not stopped. Since the beginning of, and I'll tell this to you right now, since the beginning of time, since this entire universe was created, it has been started then, and it is still happening at this very moment. Our universe is still expanding. It's not
I meant
something that,
like,
yeah.
how long does it take for it to like move away from us? Like,
How
does it happen within a year or like?
no, Monami, it is you know how when you're traveling at a constant speed,
Yes.
it's something that is constantly happening, right? So for example, if it from the moment, the very moment our solar system was formed, the everything started moving away from the moment it was formed, like literally. Then that's what we're going to talk about over here, right? You know, you have your Big Bang theory. So the scientists actually say that from the Big Bang that took place, at that particular Big Bang, the universe started expanding, and it is still expanding. So it is still happening, right? It's a constant process. It's not like it start once our planet. So the moment our planet was formed, immediately after that, it started happening. So it's not something that started happening like after 1 day, 2 day, 3 day. The moment the universe was formed, it started happening. And it has been happening since then. So from the moment, the very time where the universe was made, where our planet was made, since then it has been constantly happening. Okay, so it's not like something you can relate to time. It is a constant process that has been happening non-stop from the very first second. Okay,
Understood,
then
Miss.
one thing you have to know over is that in your syllabus, they want you to be able to describe how the red shift provides evidence for Big Bang theory. Okay, so of course, for a long time, we had a question that was how the universe is expanding. So the scientists came up with two theories, and One of the theories was Big Bang. So of course, up till now, when we take a look into it, there are still a lot of, controversies. A lot of people don't really believe it. There are still a lot of other things going on. But generally speaking, you just have to know how the scientists explain it or what is the evidence they have for it. So the theory states that the universe is expanding after exploding suddenly from a very small and extremely hot and dense region. Okay, so you had a very small and extremely hot and dense region, and from that there was a sudden explosion, and that explosion created space, it created time, and it created matter. Space, time, and matter, and that is how our universe was formed. Now, when we talk about it, you just have to know what evidence do we have or how can we use redshift to explain Big Bang. Now, if a Big Bang took place, if there was a Big Bang, that means there was a sudden explosion. If there was a sudden explosion, that means that you had a small particle, and from the small particle, there was a sudden explosion, and everything started to move away. Right? The universe, once the Big Bang took place, everything started to move away. Right? That is the Big Bang, that you had a sudden explosion, and from that explosion, everything started to move away, and that is how the universe was created. So the scientists needed evidence for the explosion. They needed to show that the universe was expanding. Right? They needed to show that there was a full explosion and the universe is expanding. So they wanted to talk about that. Now, but they could not find any proof. The proof came in the form of cosmic microwave background radiation. What is cosmic microwave background radiation? We have this low level radiation constantly present in our space. We have this low level radiation constantly present in the background, constantly. And this is microwave. If you look at the electromagnetic spectrum, it falls in the microwave region. And we have this and we have this what do you call it, we have this background radiation, and this background radiation was what the scientists detected at first. So when the scientists detected the background radiation, they said, oh, if we can look at the red shift of the background radiation, we can prove that Big Bang explosion actually took place, or the Big Bang is actually real. So what they did ahead and they did was they started taking a look at the background radiation. And when they talked about it, they actually, hold on, just give me 1 minute. So what the scientists were actually talking about is that if the universe began in a Big Bang, then high energy electromagnetic radiation should have been produced very soon after the universe began. So that is what the scientists concluded, that if the universe began as a Big Bang, then electromagnetic radiation would have been produced immediately afterwards. Now, they concluded, the scientists did some calculation, and they said that if the Big Bang actually took place, by now that electromagnetic radiation should have stretched out. That electromagnetic radiation should have stretched out, and the wavelength should have increased. A red shift should have taken place, and that electromagnetic radiation should have become a low energy radiation. So that is what they concluded, that at the start, at your start of the Big Bang, there would be high energy of electromagnetic radiation that would be produced, high energy electromagnetic radiation. But after so many years, after million and billion of years, that high energy electromagnetic radiation should have undergone a should have undergone a red shift, and it should have turned into a longer wavelength, and it should have turned into a low energy radiation. Then eventually they discovered microwave background radiation. They discovered this low level radiation in the background that was low energy, that was matching the microwave section of the electromagnetic spectrum. And this was the proof they needed. So they said, this is the original electromagnetic radiation that was produced at the Big Bang. And as you can see, it has stretched out. It has undergone a red shift. And because it has undergone a red shift, it has turned into the background radiation that we know now. So this is the evidence that the scientists had, that they are using to prove that the Big Bang theory is actually real. Making sense?
Yes, miss.
Okay, so that is basically all you have to do in your topic of space physics. Okay. Okay, no, that is not all we have to do. We have to go over our solar system. So we have to go over our solar system, in which we have to talk about our in topic of Earth. Okay, we have to talk about orbital speed. How can you calculate orbital speed? We have to go ahead and talk about our gravitational field. We have to talk about our solar system in more detail. So okay, Monami, I think we'll stop. We're here for today, and we are then going to continue on with the next part on our space physics in the next class. Okay.
All right,
So
miss.
we have done stars and universe. This is stars and universe in your syllabus, and the Earth and solar system will then go ahead and start in the next class when we have more time to go over it. Okay.
Okay.